Hello friends, in this video I'd like to solve the following problem from the International Mathematical Olympiad 1969, long-listed problem 35, proposed by Hungary. We wish to prove that 1 plus 1 over 2 to the 2 cubed plus 1 over 3 cubed and so on up to 1 over n cubed is strictly less than 5 over 4 for all positive integers n. So it's an interesting problem. Here are my hints. First, notice this inequality that k cubed is strictly greater than k cubed minus k for all positive integers k, which allows us to write this and also to write this inequality because of a denominator. Let's suppose that k is greater than or equal to. Next, use the partial fraction decomposition of this fraction, and finally some telescoping may be going on after this estimation. So give this problem a try. Alright, so as I said, obviously k cubed is greater than k cubed minus k, which is k minus 1, k plus 1, or k greater than or equal to, let's say. So 1 over k cubed is less than 1 over k minus 1, k plus 1, or k greater than or equal to. And now it's time to make use of a partial fraction decomposition. So we take our fraction, we look at the roots of the denominator. We have 3 roots, 1, 0, and minus 1. And now we need to find real numbers which will satisfy this equation. And how can we do it? Well, we can write a, b, c in these places, and we can multiply by k minus 1, k plus 1. So we will have 1 equals a, k plus 1, b, k minus 1, k plus 1, plus c, k minus 1, k. And now let's see. We have a k squared, we will have also b k squared, and we will have c k squared. We will also have plus ak and minus ck. And what about the terms without k? Without k will be minus b. And now this equality should hold for every real number k. It's a polynomial identity. So we must have the following 3 equations. A plus b plus c must be 0. A minus c must be also 0. And the minus b must be equal 1. Is it right? Let me take a look. Yes, it is. All right. And now it's easy to see the solutions. A, b, and c. B equals minus 1. A equals c. So a and c must be equal 1/2 because of the first equation. All right. So we have our partial fraction decomposition. It equals 1/2. We can put 1/2 in front. So we have 1/2 k minus 1 minus 2 over k plus 1 over k plus 1. All right. And now let's take our sum. K goes from 1 to k, 1 over k cubed. Because of our estimates, we can actually first write 1 in front, and then we have sum going from k equals 2 to n, 1 over k cubed. Now we can estimate it. sum going from k equals 2 to n, 1 over k minus 1, k plus 1. Because of our partial fraction decomposition, we can decompose it into 3 sums. So we have sum going 1/2, sum going from 2 to n, 1 over k minus 1. Then we have sum going from k equals 2 to n of 1 over k. And finally, we have sum 1/2, sum going from k equals 2 to n, 1 over k plus 1. All right, and now let's shift our indices of summation to make the same fractions. So I will take my first sum, and instead of k, I will put k plus 1. So k plus 1 goes from 2 to k plus 1 equals n. So, and here we also have, instead of k, we have k plus 1. The second sum will stay as it is. And finally, the last sum will go, I will shift, I will put k minus 1 instead of k. So k minus 1 goes from 2 to n, and our fraction is 1 over k minus 1 plus 1. Perfect. So we have sum going from 1 to n minus 1 of 1 over k, minus sum going from k equals 2 to n of 1 over k. And finally, we have plus 1/2, sum going from k equals 3 to n plus 1 of 1 over k. And notice that these sums are almost the same, but they differ by some indices. So I will make common sum from k equals 3 to n plus 1, to n minus 1. So from the first sum, I will take first term apart and second term also apart from k equals 1 and k equals 2. So we have sum going from 3 to n minus 1, 1 over k. From the second sum, I will take k equals 2 apart. I will take also 1 over n apart. And I will have sum going from k equals 3, n minus 1, 1 over k. And finally, the last sum will put 1/2, 1 over n, and 1/2 n plus 1 apart. And I will have sum going from k equals 3, n minus 1, 1 over k. All right, now cancellations are possible. First, here we have 1/2 minus 1/2. It is gone. Our sum, here we have 1/2 times our sum. Here we have minus our sum, and again plus 1/2 our sum. So after these simplifications, we have 5 over 4. And what do we also have? We have minus 1 over n plus 1 over 2n. So it's minus 1 over 2n plus 1 over 2 n plus 1. And actually, I will put minus in front. Why not? And notice that this fraction right here is greater than 0. So we are subtracting something greater than 0. So the whole thing is definitely strictly less than 5 over 4, which happens to be exactly what we wanted to demonstrate. And this really closes our proof. All right, so thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.